Hi, I'm Dr.J.Beny, Assistant Professor, Department of Mathematics, Holy Cross College, Tiruchirappalli. I'm going to discuss the topic groups. At the end of the session, students able to understand the concept of binary operations with sets, to understand the concept of groups, to learn the examples for proving the axioms of groups, and to know about which are the sets to be satisfied for proving groups and abelian groups. Introduction of groups. In mathematics, a group is a set equipped with an by operations that combines any two elements to form a third element, while being associative as well as having an identity element and inverse exists. These three conditions called group axiom, and it holds not only for number system and many other mathematical structure. Definitions of binary operations. Let G be a set. A binary operations on G is a function that assigns each ordered pair of elements of G is an element of G. For example, if you are taking two elements A comma B belongs in G, there exists an element AB also belongs in G. Definition of groups. Let G be a set together with the binary operations that assigns to each ordered pair A comma B of elements of G is an element in G, and it is also denoted by AP. And the following three properties are satisfied for a group. One is associativity, identity element exists, and the inverse exists. So here for identity element, we are taking three elements A, B, C. So this is a axiom for under multiplication. A dot B dot C equal to A dot B C. For all A, B, C belongs in G. For identity property, there exists an element E in G such that AE equal to EA equal to A for all A in G. For inverse property, for each element A in G, there is an element B in G such that AB equal to BA equal to E. Here, B is the inverse of A. Here, A is the inverse of B. Abelian and non-abelian. A group G is said to be abelian means it's satisfying the condition that AB equal to BA for all elements AB belongs in G. This is for under multiplication. Suppose if it is under addition means A plus B equal to B plus A. If non-abelian means AB not equal to BA as well as A plus B not equal to B plus C. Example, set of all integers, set of all rational numbers, set of all real numbers are all groups under ordinary addition. For addition, the identity element is 0 and the inverse of the particular element is negative of that element. For example, if you are taking the element 2 means the inverse of 2 is minus 2. If you are taking 3 means the inverse of 3 is minus 3. So let me check, is it is a group under addition or not? So Z is a group under addition. Here I'm defining the set Z. I'm checking the four axioms should be satisfied or not. Closure property. So I'm taking two elements from this set. So the output is also belongs in this. Here 3 plus 5 equal to 8. So 8 exists in this group. Associative property A plus B plus C equal to A plus B plus C. So total count is 15. 15 belongs in this group or not? Belongs. Identity element, what is the property? A plus identity element is equal to A. So under addition, I for the identity element, which element is 0? So let me check whether 0 exists in this set or not. Exists. So therefore, it belongs. Then inverse. I'm taking 3. The inverse of 3 is negative of 3, minus 3. So minus 3 also exists in this set. So belongs in the set. So therefore, we can say Z plus is a group under addition. So let me check Z plus is a abelian group under addition or not. So what is the one more condition for abelian? Along this property, we want to satisfy the commutative property also. So look at here. So here I am only checking the commutative property because here all the axioms are satisfied, isn't it? So 3 plus 2, A plus B equal to B plus C. So for both the term, the answer is 5. 5 belongs in this set. So Z is a abelian group under addition. Example 3. The set of all natural numbers a group under ordinary addition. So I'm defining the set n, set of all natural numbers. Look at here. For under addition, 0 is the identity element, isn't it? So 0 does not exist. So identity element does not hold. For, if I am taking 3, the inverse of 3 is what? Minus 3. So minus 3 also does not. So the 2 axiom does not. So therefore we can say n is not a group under addition. Here I am taking the example set of integers under the usual multiplication is not a group. So look at here, for multiplication, identity element is 1. So 1 belongs in the set. Then we check the inverse element exists or not. Look at 1. So inverse of 1, 1 by 1 exists. Inverse of minus 1 into 1 by minus 1, minus minus getting cancelled, you get 1. So other than this 2 element, remaining element does not exist. Suppose I am taking 2. So the inverse of 2 is what? 1 by 2. Then only you get 2 getting cancelled, you get the identity element. So 1 by 2 exists or not? 1 by 2 is 0. So 0.5 does not exist in integer, isn't it? So therefore the set Z is not a group under multiplication. A conclusion, here we learn sets with the binary operation, lot of examples for proving groups, and identify which are the sets to be groups and abelian groups. These are the frequently asked questions. These are references.